We'll continue with our investigation of applications of integrals by examining how we can use integrals to find the area between two curves rather than between one curve and the x-axis. So to start out, let's consider a curve and a curve that runs below it. Okay, this is, let's make this first curve f of x, and the second curve will be g of x. Okay, and we're going to consider the region between A and B. And so let's say we want to find the area between the two curves. Well, let's see. If we were to find the area of just the curve under f of x, the area just under f of x, it would be this yellow area here. Okay, and what we want is to find the area that is under f of x but above g of x. So that's going to be this area right here. Okay, now we notice that this is the same as the area under f of x take away the yellow area because area subtracts. So it would be, to get the area in just the top piece, we want the whole area minus the bottom area. Okay, so what we are going to do is define the area between f of x and g of x, and note that it is equal to the area under f of x minus the area under g of x. And that will be the area between them. So the area that's under f of x that's not under g of x. Okay, so in an integration, using integration, we can write the formula for this as area between two curves is equal to the integral from a to b of f of x dx, that's the area under f of x, minus the integral from a to b of g of x dx, which is the area under g of x. And because of our rule about integral subtraction, we can actually write that as a single integral. So this is f of x minus g of x dx. Okay, so now we have to be a little bit careful here. So you notice in the picture that we've drawn, f of x is greater than or equal to g of x at all times in the region that we're looking at. So we need to have the stipulation because when we're computing the area of a shaded region or the area between two curves, we want our area to be positive. We're talking about geometric area, not net signed area as we are with integrals. So we have to put in the caveat that f of x must be greater than or equal to g of x for all x on the interval under discussion. Okay, so what happens if we want to find an area where that is not true? Let's say we have two functions, f and g. They do something fun like that. And then g of x goes there. So let's say this is f of x, and then this one is g of x. So sometimes f of x is above, sometimes g of x is above. So what we need to do is we're looking at these areas in two different ways. So for this area, the yellow portion of the area, f of x is the higher function. And for this area, g of x, this blue area, g of x is the higher function. So what we need to do is, let's say we're taking it from point A to point B. For every region that we're taking the integral of, we need to make sure, and this would be point C here, where C is the point of intersection, or the point where they switch, where one becomes lower, the one that was higher becomes lower. And that's always going to happen as long as we have a continuous function, which we need to take the definite integral anyway. That's going to happen at a point of intersection. So we have A, C, B. That's actually a consequence of the intermediate value theorem. So what we're going to do is we're just going to take two separate integrals. So in this case, we're going to take the integral from a to c of f of x minus g of x because here f of x is higher, dx, plus the integral from c to b of g of x minus f of x dx. Okay, and another way we could write this is that the area, so here this is one way of putting the area, or the area could be the integral from a to b of the absolute value of f of x minus g of x dx. But since we usually evaluate absolute value integrals by separating them into piecewise functions a, usually a is somewhat more efficient. And there's a situation that you might think would change things, but it actually doesn't. So let's say we have an f of x that's above the x-axis, and we have a g of x that's below. Okay, and we're looking at the region from A to B. Okay, so we're trying to find this area. So our area is still here just going to be the integral from A to B of f of x minus g of x dx. Because we don't right here, the area below the x-axis will come out as negative, but we are subtracting the function. So all we're getting is we're going to get a difference. So if we have a positive minus a negative, we will get a bigger positive difference. So we're actually going to get a positive value for the difference, even though g of x is going to be below the x-axis at all times. Okay, let's see how this works. Example 1. Find the area bounded above by y equals 3x plus 2 and below by y equals x cubed minus 1 on the interval between 0 and 2. So let's just check and confirm these functions are both increasing on that interval. If we take the derivative, we can see that they're actually always increasing on that positive interval. And what we are going to want to do is look at, in fact, x cubed is always increasing, and so is 3x plus 2. So let's check at 0, y is 2 and y is minus 1, so y equals 3x plus 2 is bigger. And 2, we have 2 times 3 is 6, plus 2 is 8. So we have 8, and then we have x cubed minus 1 is 7. So that's still going to be higher. So we can trust the problem expression that the y equals 3x plus 2 is going to be on top for this region. So that's our f of x, and that the y equals x cubed minus 1 is going to be below that. So that'll be our g of x. So our area is equal to the integral from 0 to 2 of 3x plus 2 minus x cubed minus 1 dx, okay, which is equal to the integral from 0 to 2, and we're just going to write this all out. We have 3x plus 2 minus a minus 1, so that's a plus 3 minus x cubed, so we'll put the minus x cubed first, plus 3x plus 3 dx. Now we're ready to integrate, so this is equal to minus x to the 4th over 4 plus 3x squared over 2 plus 3x. And that's all going to be evaluated from 0 to 2. Okay, so this is minus 2 to the 4th. We're going to do the 2 to the 4th part first, though, plus 3 times 2 squared, 2 plus 3 times 2, minus, and this, since there's all x's in there, it just comes out 0. Okay, which gives us minus 4 plus 6 plus 6, so that's 12, take away 4, which is 8. Okay, and our answer came out positive. In these area problems, your answer should, this is a good kind of just quick mental check. If your answer is not coming out positive, then something is wrong in either your calculations or in your setup. So you do need to make sure that these areas are coming out positive. Okay, let's look at another example. And sometimes you will not be given a region and you have to work some stuff out. So we want to find the area of the region bounded by y equals x squared and y equals 2x minus x squared. Okay, so this is going to be a situation where I'm going to try to sketch this because we're not given any bounds for a and b. We just want to try to find the area bounded. So I'm going to sketch a parabola. You never allowed to forget how to sketch a parabola. That's my y equals x squared. Y equals 2x minus 2. I have two roots. So my roots are x equals, so I have 2 minus x times x. So I have a root at x equals 2, and I have a root at x equals 0. So you can make that, oops, didn't mean to erase my whole axis. Let's go 2. So I have a root at x equals 2, and I have a root at x equals 0. So that's a downward opening parabola because it is a negative x squared. So I'm looking for the region right in here. So what I want to do is I want to find the points of intersection of this parabola. So if I know here to here what those 2 points are, I'll know the x values of my a and b. So how do I find the points of intersection of a parabola? Well, I set them equal to each other. So I have x squared equals 2x minus x squared. So when I add x squared to both sides, I get 2x squared. Subtract over there. Y equals 2x minus 2x squared. So 0 is 2x times 1 minus x. So my solutions are x equals 0 and x equals 1. And that is the most important thing to figure out right here is what my x coordinates are. I don't actually need to find the y coordinates because the reason I was interested in them is just to see what those points of intersection are. And I notice that the function that's on top is the second function. So that's going to be the function that I have first when I'm doing my subtraction. Okay? So we know that that is higher. Okay, and if you want to, you can check a point in the middle, but in this case, we really don't have to. We know what our functions look like. So we are going to do the integral from 0 to 1. That was why we did that whole calculation. And we are going to take the 2x minus x squared, and then we're going to subtract another x squared. Minus x squared dx. Simplifying, we get the integral from 0 to 1 of 2x minus 2x squared dx. So we can, right, this is x squared minus 2x squared cubed over 3. We're going to be evaluating that from 0 to 1. So we get 1 minus 2/3 minus 0. When we plug in 0 and it's all x's, it's just 0. And that is equal to 1/3. Okay, last one. What happens when we have something that gets a little weird and a little funky? Okay, so example 3. We're going to find the area of the region bounded by x equals 1, x equals 4, y1 equals 2x cubed minus 16x squared plus 30x, and y2 equals negative x cubed plus 9x squared minus 18x. Okay, so let's take a look. We've got two lovely cubic functions. And we want the area of the region bounded by y equals x equals 1, x equals 4. So we know ultimately we're integrating from x equals 1 to 4. But we need to know about points of intersection, where these intersect, which one is greater. We need to know a little bit more about this situation. So the first thing we're going to do is try to sketch a graph. And in order to try to sketch the graph, the very first thing we want to do is try to come up with where the zeros are and if there are any zeros on these regions. So let's look at y1. Okay, y1 is 2x cubed minus 16x squared plus 30x. So y1 we can factor out at 2x. So we have 2x times x squared minus 8x plus 15. And that factors to 2x times x minus 5 times x minus 3. So this one has zeros at, so x-intercepts are 0, 3, and 5. Okay, so that is my y1. So I'm going to put x-intercepts at 0, and then 1, 2, 3, 4, 5. So 0, I'll put 6 just in case, 1, 2, 3, and 5. And this one has a positive leading coefficient, so it's going to be a positive cubic, which means it starts down and goes up, so it's going to look something like that. Don't know if that's exactly correct, but it's close enough for our purposes. We don't actually have to calculate like the maximum or anything like that because we mostly just need to know where one is above the other. Okay, and then y2. We can factor out a negative x, which leaves us with x squared minus 9x plus 18. Factoring that, we get minus x times x minus 3 times x minus 6. So that means we have roots at 0, our x-intercepts at 0, 3, and 6. So I have 0, 3, and then I have 6 again. This time we have a downward cubic, so it's going to look like this. Okay, and then we are going to go and go down like that. Okay, and so one of the things that we'll notice is that because one is positive and one is negative here, and they don't cross until 5, it doesn't really matter where this point of intersection is because it's not going to happen before 5. It has to be at least 5 where one of them will cross the x-axis. So we can, because we're only integrating between 1 and 4, we actually have the only point of intersection that's going to occur within the area that we are integrating. So we're integrating right in here, and we know they're not going to cross again until at least 5. So we're okay with just trying to find this area that I've shaded in blue. So that's the area we're looking for. So in the first, for the first bit, so this is maybe not in highlighter. This is 3. And this is 1, and this is 4. So we're going to do one integral from 1 to 3. This is our y1, where our y1 is on top. And then from 3 to 4, y2 is the function that's on top. So our first integral that we're going to set up, so we'll set up our integral for the area. The first integral is the integral from 1 to 3. And it's going to be of y1 minus y2 dx. And we're going to add the integral from 3 to 4 of y2 minus y1 dx. Okay, so let's plug in all our lovely numbers. So the integral from 1 to 3, we're going to subtract y1 and y2, so that's 3x cubed minus 25x squared plus 48x. Plus the integral, and that's dx, plus the integral from 3 to 4 of negative 3x cubed plus 25x squared minus 48x dx. And you notice you just get the negative because you're subtracting the other way around. That's our area, and this is equal to, when we integrate, we get, that's a cubed, sorry, a little hard to see, 3/4 x to the 4th minus 25 thirds x cubed plus 24x squared. And we're going to evaluate that one from 1 to 3, plus the negative 3/4 x to the 4th plus 25/3 x cubed minus 24x squared. And evaluate that from 4 to 3. And that equals 243 over 4 minus 225 plus 216 minus 3/4 minus 25/3 plus 24 plus negative 192 plus 1600 over 3 minus 384 minus, and we'll just continue on over here, minus negative 243 over 4 plus 225 minus 216. And I leave the rest of the calculations to you. Have fun. And this is about as yucky as it gets for numbers. So generally when I give you numbers like that, a decimal answer approximation will be just fine.